Okay, everybody, I've got 12 o'clock Central Time on my clock here. I'd like to welcome everybody for joining us. My name is Allie Trollier, and I'm with ECO2. It's Eco-Oxygen Technology. Today is Tuesday, and we're going to be beginning our second session of this webcast that we're doing throughout the summer. The last one we did in June was on H2S and collections, and today we're going to be exploring a new topic that is secondary clarifier superoxygenation. And what we're going to be talking about is a way for plants that are overloaded to get greater capacity for BOD removal. Also for preventing rising sludge in a clarifier due to nitrification, and a couple of other interesting ways that you can use this method for possibly solving some biomass problems at your plant. So with that in mind, I see we've got a few more people jumping on, and so I'd like to welcome those late visitors. And just a few housekeeping items before we get going. All of the attendees will be muted during this session, and so we will only hear from the presenters, myself, and the one and only Dr. Speece, who's joining us today live. So what we're going to do is we're going to go through this technical presentation, and if you have any comments or any questions or any problems, you can type them into the question box at the side of your screen, and we will answer those at the end of the technical portion. We're scheduled for 30 minutes, and so after completion of this session, you'll get an email with a copy of the presentation and a certificate of completion that you can use for an ongoing education credit. So we're going to continue through a little introduction, and then we will have the privilege of hearing directly from Dr. Speece. So I'm going to minimize my webcam. It's really good to see you all, and I really appreciate you all coming. All right, without further ado, let's dig in. We're going to be talking about some really interesting topics that maybe you haven't heard of before, but I'm just going to give you a little bit of an introduction of what we're going to talk about as far as a new topic, and I'll cover some of the basics just to give you a little primer. But the real objective for today's session is to provide wastewater professionals, you all, with another tool in the toolbox and a new way to think about biomass and conventional activated sludge processes. So I'm going to go through a little intro, and then I'm going to introduce Dr. Speece, and he's going to talk about the theory of this new topic, secondary clarifier superoxygenation, and what it means to convert your clarifier to an oxic bioreactor, and some common problems that this may present a solution for. And he's going to go through a couple examples and then flip it back to me, and I'll give you a couple resources, and we'll do the Q&A. So a quick introduction to ECO2. We're the home of the Speece Cone, and we're located in Indianapolis, and everything is made in the U.S. There's a picture of basically our entire team. We're a group of engineers, and we work solely with this one technology that was invented by Dr. Speece. So there in the photograph, you can see me on the left. I'm Allie. Next to me is our engineering director, Kevin Jacobs. Next to him is Ryan Grimes out of the West, and our president and longtime ECO2 champion, David Kleidens. And then our national sales manager at the end there, Clay Thompson. And of course, you can see a photograph of Dr. Speece at the right. Also, we're really excited to celebrate 20 years in operation this year, with the company being founded in the year 2000. So let's take a look at what ECO2 does. It's superoxygenation for the most part is what we're doing. And what that is, it's raising the dissolved oxygen level using pure oxygen, not air. And an important thing to note with this technology is that we're maintaining that oxygen dissolved level below saturation, below the 100% saturation. So we want to make sure that all of that oxygen stays dissolved and does not effervesce out of solution. So just a little bit of history, the known benefits of pure oxygen have been around for a long time, and historically, oxygen has been difficult to dissolve for a few reasons. There's relatively low oxygen gas solubility for oxygen gas, and then also the devices in the past have had poor performance, maintenance, efficiencies, things like spargers and nozzles, until the invention of the Speece Cone in 1994, which Dr. Speece is going to tell you is called the downflow bubble contactor, and it's published in this book that you can see there. But the photograph on the right is an example of this 20 years in business. So Cripe Engineering incubated ECO2 back in 2000, and today we've got over 100 installations, and the largest one is pictured there at the right, and this is multiple large Speece cones on the Savannah River that are adding dissolved oxygen to the harbor. Now, in addition to that harbor application, we've got a lot of different points of application within wastewater and drinking water itself. Now, we've covered one last month. You can see up here, the top first one was odor and corrosion control in wastewater collection systems, also headworks and primary clarifiers. We covered that last month. So this month, we're going to take a look at this topic, the secondary clarifier superoxygenation for biomass enhancement. And we've got a couple other applications that we'll investigate as the summer goes on. We also have projects in wetlands, lakes, rivers, also in oil and gas. And we also use the Speece Cone for dissolving carbon dioxide in drinking water processes. But with all that said, what is superoxygenation? Well, it requires two main components. On the left, you've got to have an oxygen supply, and then you have to have a good way to dissolve it, which is shown on the right here. This is the Speece Cone. So you've got to get the oxygen, and then you've got to dissolve it into the water. I'm going to show you what this looks like. When we talk about the oxygen supply, there's two options here. You can purchase it from a local supplier, and they deliver it in a truck, and you store it on site in a double wall vacuum insulated tank, and it goes through an evaporator and turns back into a gas, and then we're able to dissolve that oxygen gas in the water. Alternatively, for a capital expense, and if you've got a good maintenance crew, this might be a good option for you to make the oxygen gas on site or just concentrate it from ambient air. Those are the two options of getting the oxygen. But then putting that oxygen efficiently and effectively into the water is what we do at ECO2. So this is a mock-up of what the system might look like, and they come from very small to extremely large systems, all based on the demands of the site. So let's take a look at what this side stream looks like. We're basically tapping off of a conveyance pipeline for this side stream process. So we would tap off of either a collection line, or today we're going to be talking about a mixed liquor line from an aeration basin over to a clarifier. But at any rate, off of that conveyance pipeline, we would tap that line and draw a portion of that flow up to the top of the cone, where the oxygen gas is introduced. And as that flow moves through the cone, the oxygen gas is dissolved, and that wastewater with high dissolved oxygen content is then put back into the pipe and continues on in the process. So let's take a little bit closer look at what happens in that cone. So we talked about the water coming off of that line, going through a side stream pump, just adding enough pressure to overcome the losses of the system and get back into the pipe. So into this cone, the water is entering at a really high velocity. Picture this cone is full of water. The water is entering at a high velocity, and the oxygen gas is introduced at the top, and the water is breaking all the oxygen gas into smaller and smaller bubbles until the water leaving the cone has a velocity slower than the buoyancy velocity of the bubble. So the only way the oxygen is able to leave the cone is to dissolve. So that water with a high dissolved oxygen content is then discharged out of the cone and back into the pipe. Now, quick recap on what we talked about last month. The advantages of using oxygen over traditional chemicals are obvious cost savings, but then also results that are near zero. You can see here in the graph that may look familiar from last month, the H2S readings in parts per million on an odor logger hanging downstream of the treatment system are often over 1,000 parts per million, and they go to near zero just on day one of the ECO2 system and are near zero and have been for the next 13 years, the last 13 years in service. Also, the solution is just it's sustainable for the environment, and it's simple and easy to use for the operators. Now, switching gears just a little bit, we're going to go inside the plant. Normally, we've been talking about the collection systems, but now we're going to talk about process and mostly the conventional activated sludge process and some different things that you can do to think about problems in a new way instead of just adding or expanding. And so with that, I'd like to introduce our guest speaker. We've got the privilege today of hearing directly from the one and only Dr. Dick Speece. He's a professor emeritus at Vanderbilt University, also author, inventor, engineer, and my hero, introducing Dr. Dick Speece. And with that, I'm going to go ahead and give you keyboard and mouse control and pass it over to you. Thank you, Dick.
Thank you, Allie. I think it's important that we emphasize that there are some common water quality problems that can be readily solved using pure oxygen, but are not solvable using air. So, as Allie mentioned, now today we're going to look at another example in that category. And so we see here an aerial view of a number of small wastewater treatment plants, big ones, and so on. And the issue that I want to point out here is to notice the size of the aeration tank compared with the size of the clarifier. We see, of course, the aeration tank is sized based upon the FDM design. The secondary clarifier is generally based upon an overflow rate of, say, 750 gallon a minute per square foot, gallon per day per square foot. So that's 100 feet per day. So we look at the size of the aeration tanks, and we see here the size of the clarifiers. And the point that I want to point out here is these secondary clarifiers are in the general range of the size of the aeration tanks. So we say to ourselves, why do we have aeration tanks in the first place? And so, as I mentioned, the sizing is based upon the FDM, how many pounds of biomass do we have to maintain on the site to handle whatever pollution load comes in. So the aeration tank contains the necessary amount of biomass, and then that, of course, is the place where we transfer the oxygen. So we have to transfer a certain number of pounds of oxygen per day to meet the demand for the bacteria to aerobically remove the pollutant. So you look at this aeration tank, and in this, if you had a coarse bubble aeration tank, you would be putting in 100 cubic foot of air and dissolving only 1 cubic foot of oxygen. So you can see the turbulence there is quite high. So the characteristic is aeration tanks, lots of turbulence, clarifiers have to be something here that's very quiescent. And so after the aeration tank, then of course we need following these very turbulent conditions, we then go to a very quiescent condition, and in that quiescent condition, the bacteria are able to settle out. So to minimize the electricity consumption in the aeration tank, we would look at that and say, we keep the dissolved oxygen very low, normally less than 2 milligrams per liter. And if we keep that dissolved oxygen at 2 milligrams per liter, we satisfy the aerobic metabolism. But then we note that when we transfer that mixed liquor from the aeration tank and we put that into the secondary clarifier, we essentially have 2 milligrams per liter of DO here, and that rapidly disappears so that the aeration tank is essentially devoid of dissolved oxygen. So again, I want to emphasize, notice how quiescent the clarifiers are and how turbulent these are. So we look at that system and we say, the clarifier, great big tank, is sitting there doing one thing, and that is settling out the mixed liquor. So the next question we would ask is, relatively speaking, how much of the biomass is sitting in the sludge blanket in this clarifier compared to the amount of biomass in that aeration tank? So we'll later on look to see that relative fraction, but because the solids sitting in this secondary clarifier are not oxic, they are not included in the design for solids under air to achieve a certain amount of consumption of the BOD. So what if that volume in the clarifier could be used for added capacity? So next slide. In this next slide, generally at a clarifier, in a primary, the primary clarifier is generally the main odor source at a wastewater treatment plant. So generally the way we handle odor problems, this is a primary clarifier, we can either cover the tank, pull gases out of the tank and scrub them, so we allow the odor to form before we scrubbed it. And we're saying here, the other alternative is to prevent the odor from forming in the aeration, in the primary clarifier altogether, by keeping the oxygen content in that clarifier positive, so that no hydrogen sulfide is able to be formed. So we have accomplished two things. One is we have maintained the quiescent conditions in the clarifier, and the other is we have now made that oxic. So since it has been demonstrated that we can superoxygenate the primary clarifier to prevent odor generation, now we look at the application here. What if we did the same thing to a secondary clarifier? If we could do that, there we could increase the aeration capacity of the total plant. In the winter time, we could increase the biomass, or the solids retention time. If a plant needed to have a lower loading rate for phosphate removal, we could increase we could lower the loading rate. And then of course we could prevent denitrification from taking place in a secondary clarifier. So by maintaining oxic conditions here, primarily we are increasing the SRT and reducing the F to M. Next slide. So the question we look at in this next slide is, what is the relative amount of biomass that sits in the clarifier compared to the relative amount of biomass in the aeration tank? So we would look at the aeration tank and say, if, for instance, the BOD coming in was 250 milligrams per liter, that would be a food ratio of, we would require having 2,100 pounds of BOD for every MGD into the plant. And if we design this aeration system for an FDM of 0.5, then we would need 4,200 pounds of biomass in the aeration tank per MGD. So we take a look at the secondary clarifier. We have 2 milligrams per liter going in. Very quickly it's consumed. So if the secondary clarifier was designed for an overflow rate of 750 gallons a day per square foot, and if the sludge blanket was 5 feet deep, let's say that we have a return sludge concentration of 9,000, and let's say we assume that the average concentration in that sludge blanket is 6,000 milligram per liter. Under those conditions, we would have 2,500 pounds of biomass sitting in the secondary clarifier, which is not oxic and therefore not able to enter into aerobic metabolism. So next slide, we look at this and say, okay, what if we imagine the same wastewater treatment plant and the same operating conditions with just one change? Let's say we could raise the DO concentration in the clarifier influent to 40 milligram per liter. We could raise it to 60, but let's say we raised it to 40 milligram per liter. We would now still have the 4,200 pounds of biomass in the aeration tank under air. But when we look at the secondary clarifier, now we see that that 2,500 pounds of solid sitting in the secondary clarifier is now oxic. And so the biomass under air now goes from the 4,200 here and the 2,500 here. So now we have 6,700 pounds of biomass per MGD in that plant. And we have increased the capacity of that plant by 60% simply by doing something to the influent to the secondary clarifier. So if the plant was operated and was designed for an FDM of 0.5, now we've dropped the plant FDM ratio down to 0.3. So let's look at the next slide here. So we say it's going to vary whatever this oxygen uptake rate is in the sludge blanket. At the head end of the aeration tank, there might be an oxygen uptake rate of 100 milligrams per liter per hour with the readily degradable food coming in. And at the head end of the aeration tank, we have a lot of the BOD is taken out rather quickly by either attachment of the colloids to the biomass or taking inside the soluble compound. So if we look, let's say this is 15 feet deep. So the DO saturation at the bottom of a 15-foot depth water column here would be about 65 milligrams per liter. So that the water is still undersaturated with respect to the pure oxygen dissolved. So we are preventing any effervescent loss of the DO when we go up to these very high conditions here. And so the reason for that is we are bringing the mixed liquor in with all of the dissolved oxygen dissolved. No bubbles are involved in this. If they were, of course, we would get dissolved air flotation and we would ruin the whole process here of gravity settling. So by doing this, the sludge now has another opportunity or additional opportunity to aerobically metabolize so that when the returned sludge is brought back to the head end of the aeration tank, all of the stored BOD has been removed. We essentially have the bugs hungry again. And so we look at this and we'd say, this kind of an application would be ideal for a treatment plant that is overloaded, but doesn't have the physical space to expand. So let's go to the next slide. So as anyone watching says, well, that's just the contact stabilization process, and we say that's right. So in the contact stabilization process, we take out the BOD here, and then we have a separate tank down here that essentially metabolizes that BOD aerobically, so the bugs are hungry by the time they get back here. So all we're doing is having a contact stabilization process here, but we are not requiring an extra tank to aerate it. We're essentially just using the existing tank that's there, in order to carry about that contact stabilization process. So the next slide, please. In this slide, we would like to summarize here, and the summarizing says we raised the DO to a very high level compared to what the 2 milligram per liter we're normally associated with, but we keep it below saturation so that it is kept in solution and not lost. And we have increased by making the secondary clarifier oxic. We've increased the capacity of the plant by increasing the SRT. We've improved if wintertime nitrification is a problem, or if we need additional SRT to achieve stabilization, then that is accomplished without the addition of any additional tankage. So the point of this clarifier, of this webinar, the technology is available to convert a quiescent secondary clarifier into an anoxic bioreactor. We do this by the technology that we have over 100 installations with, and we do not alter, we do not destroy the quiescent conditions that are necessary to carry out the secondary clarifier function, but we do significantly increase the solids under air. So we would like to invite you to listen in next month to another chapter in ways of using pure oxygen to solve a water quality problem that cannot be solved with air. And we think you'll find this next presentation interesting. Even you might find it revolutionary. So thank you, and we hope you'll dial in next month.
Awesome. Okay, Dick, thank you so much. I really appreciate you going through that for us. I'm going to go through just a couple more slides here. We got about 3 minutes. If any of these problems sound familiar to anyone attending, we've got a couple of handouts. I'd like to draw your attention to one of them here. It's called the application note, and that has more information like what we had covered. And you can see some of the information from today, and then you can also contact us at any point. Also, like I pointed out in the beginning, you will be receiving an email after this presentation that will have a link to view the recording again, and a copy of the presentation, as well as a certificate for the 1/2 hour. Also, I'd like to just draw your attention to the website, eco2tech.com/news is where we've got some updated videos, new case studies, and our contact information. Also, tune in for our next session, which is going to be investigating a little bit more on the solids side of the plant. Now, I'd like to just kind of show you our contact information, and then we've got a couple of questions here. And so I think we've still got Dr. Speece on the line. And so I'd like to ask you these questions, Dr. Speece. Let me see if I can get my webcam back. And okay. Hi, everybody. All right, our first question is, would the clarifier need to be resized to handle more sludge? Can you answer that for us?
Essentially, no resizing would be required to achieve this 60% increase in aerobic biometabolism. And we think that's one of the main advantages, because there are many plants that are facing the problem of no extra real estate available. So this is a particularly neat solution to a plant that needs more capacity but doesn't have more land to expand. So the answer, no. The clarifier is used just like the same design as if it's not used for aerobic metabolism.
Okay, so we're not really making changes to the flow or the contents. We're just changing the condition of the sludge in that digest or in that clarifier.
Right.
Okay, great. We do have another question here, kind of on a similar beat. Will this affect my solids handling, or could I increase my sludge blanket depth?
That's the next question that anyone looking at this would say, and the answer to that is why not?
Wonderful. I would love to explore that more. Maybe we can do that on an individual basis with any other interested parties. Also, the last question I see here is, are full-scale case studies available to demonstrate proof of this concept? And Dick, I think I might field this one if you don't mind. We do have the full-scale case study for the primary clarifier superoxygenation that was in Maine, Madison, Maine. However, we do not yet have a full-scale case study for superoxygenation of a secondary clarifier, but we are really open to looking for that pilot case study and a partner to work with where we can do some of this testing. So with that being said, we did have one more question that just came up. This is going to be a toughie, but it says, what is the rough cost for basically a rough cost for adding this technology? Tough to answer, but I guess, would you mind responding to that for us, Dick?
That, of course, is the relevant question. The answer to that question is going to be very individual. What is the need for increase? How much increase needs to be made? And so we can't give you that information unless we know the particular installation that you're making reference to.
Right. That is a hard one, but I would love to get into just even providing some budgetary estimates for anyone who's interested based on what the parameters, size, flow, oxygen demand, all that are. Yeah. Okay, we did get another one. Is it just the side stream that is oxygenated? Would you, I guess, Dick, would you say run that full mixed liquor pipe through, or would you want to just stick to the side stream concept?
I think the most common issue would be we would take the full stream, raise the dissolved oxygen, and put it into the secondary clarifier. There may be cases where we would use a side stream and raise the DO much higher, but I think for most installations here, we're capable of doing this in the mainstream, getting the dissolved oxygen to the level that's required to solve the problem. So in these cases, probably we'd be using the full stream.
Okay, great, thank you. One more that just came up. Is there a minimum sludge blanket depth to maintain for this concept to work?
Of course, if you want to use this concept, we would like to have a thicker sludge blanket. Essentially, no. There are some people who like to maintain the minimum sludge blanket because they feel more comfortable operating with the top of the sludge blanket being a long ways from the overflow weir. However, some operators feel like with a thicker sludge blanket, they actually get more filtering of suspended solids and get a better quality of effluent. So the issue is there's no minimum requirement to do this, and it would depend how much extra biomass do you need to achieve the loading rate that you have. So that would be dependent on your condition as well.
A lot of fun things to explore with this new tool in the tool bag. What all you could do with your RAS and your WAS. We have a couple more questions coming online, but I think it's going to start getting over our time period. So I'd like to invite anyone who has any additional questions to contact me directly, Trollier@eco2tech.com, or just respond to the email that you're going to be receiving shortly. Dick, it has been a real pleasure doing this with you. I hope that we can do it again soon. And for everyone who was in attendance, thank you so much for your engagement and your attendance. And please tune in again next time. Thank you.